All right, folks, we have an 8-kilogram bowling ball. It is traveling 2 meters per second to the right. It bounces off the spring and ends up traveling 2 meters per second to the left. The ball interacts with the spring for 0.25 seconds. We want to know, what is the bowling ball's change in momentum? How much force does the bowling ball experience? And then if the ball hits a pillow instead and is brought to rest in 0.25 seconds, how much force would the ball experience in that case? Okay, so we'll start off with the first situation. We've got the ball going to the right, and then it bounces to the left. Okay, so I filled in the mass of the bowling ball, which said was 8 kilograms. That's unlikely to change before and after. And when it's after it interacts with the spring, it's going in the opposite direction. And so I'm going to write the new velocity as a negative. Okay, it's going the same speed but a different direction, so it's, again, same magnitude, but the negative signifies direction. Okay, and the first thing we want to know is, what is the bowling ball's change in momentum? Okay, so the change in momentum. That's really easy to figure out. Remember, if we have the mass and velocity of an object at any point, we can calculate its momentum. So we can do that before and afterwards. So the change in momentum, the initial momentum, I should say, 8 times 2, so that is 16 kilogram meters per second, right? And then the final momentum, 8 times negative 2, so that would be negative 16 kilogram meters per second. Okay, so our impulse, right, our change in momentum, that's equal to the difference between our starting and our final. Okay, now because they are going in opposite directions, the impulse is going to be pretty big, right? So to go from 16 to negative 16, that is a difference of 32, right? The difference between 16 and negative 16 is 32. And because the change was in the negative direction, we're going to say that the impulse is a negative 32 kilogram meters per second. Okay? If this doesn't quite make sense to you, sometimes I make a little number line. If we're starting at 16 kilogram meters per second and we end up at negative 16, okay, just a number line here. All right, smack dab in the middle of 0, right? So to get from here to here, we have to lose 16, right? Go down 16, and then we have to go down another 16, right? So the difference between these two is negative 32. That's how we get our impulse. Right? Okay, so now we want to know, how much force does the bowling ball experience? Recall that we can calculate the net force if we have the object's impulse, change in momentum, and its change in time. Now, it did say that this whole ordeal took about 0.25 seconds, so we can say the change in time is 0.25 seconds. And now it's just a plug and chug, right? So the net force is equal to the change in momentum, which was negative 32. Okay, that's kilogram meters per second. And then the change in time was 0.25, so divide that by 0.25. And let's see what we get here. So I got negative 32 divided by 0.25, getting negative 128. Okay, so that is the net force. Net force, negative 128, right? That's newtons. Okay. Now this negative just tells me direction. Okay. So if I wanted to add to my diagram here a net force going in that direction of 128 newtons, okay, that would make sense, because if you're going to the right and all of a sudden you're going to the left, that means that you had to experience a force in the left direction, right? That was the direction that the change occurred. So I'm just going to rewrite net force here so I can compare this later. 128 newtons, right? Okay, so that answers the first couple of questions, right? The change in momentum and the force that the ball experiences. Now we want to know, if the ball hits a pillow and is brought to rest in 0.25 seconds, right? So instead of hitting a spring, it hits a pillow, and it comes to a complete stop, how much force would that ball experience? Now, before we do any calculations, you should be able to think about that situation. If the difference between something that's bouncing versus something that's coming to a stop, it's going to take a lot more force to get it to not only stop, but change direction, okay, than it would be to just make it stop. So if I compare that to this situation here, okay, again, everything's basically the same. We have the same mass bowling ball. It starts at 2 meters per second. The only difference is now it's going to end with a velocity of 0 meters per second. So just like before, if we want to figure out the net force acting on the ball in this case, we need to know the change in momentum and the change in time. Now, it did say that our change in time is still 0.25 seconds, which just means that now we just have to figure out our change in momentum. Okay. Again, we have the mass and velocity in both cases, so we could easily find the momentum both before and after, mass times velocity. So our initial momentum still 16, just like it was on the previous situation, but now its final momentum is 0. Okay. P is equal to 0 kilogram meters per second, because it's not moving, right? So our impulse, our change in momentum, right? That final piece that we need. The difference between 16 and 0 is negative 16. Right? Okay, so again though, if we are traveling to the right and we come to a stop, in order to change its direction, to change its speed to 0, that means that we have to experience force going in the opposite direction of motion. Okay, so on my free body diagram, I can just draw a vector, okay, that's going to bring it to a stop. Okay, so we have the change in momentum, negative 16. We have the change in time. We can again solve for the net force. Okay, so change in momentum was negative 16. Right, change in time was 0.25. Okay, and that's seconds. So negative 16 divided by 0.25 equals 64. You'll notice that this is actually half of the force that we needed from the previous question. Okay. Originally, I'll clear this out of the way. Originally, we needed 128 newtons to push it back in the opposite direction at the same speed. We're going to need exactly half of that to just bring it to a stop. Okay, and again, if you kind of refer back to your number line, that kind of makes sense, because if we're starting at positive 16, right, to get all the way from positive 16 to negative 16, we knew it took 128 newtons of force, right, in that direction. But just to go from 16 to 0, right, halfway, a change in half of that momentum, it would make sense that we require half the force, okay? Because that change in momentum is proportional to the force. Okay, the bigger the force, the shorter amount of time. If your time stays the same but your force gets bigger, okay, that means your change in momentum is going to be much bigger as well.